Bad news though, I don't have any calculations, so we just had some problems in the code that, so we don't have calculations. Good news is you're going to see a lot of equations. Hopefully that's what you came for. Yeah, so we're just going to talk about this theoretical development of high-fidelity cable models with varying length. So we'll give a little bit of introductions, why am I doing this, and then I'm just going to go through the theory here. So there's kind of two main components, which is ANCF, which is sort of the cable model that I'm using. It's kind of more an FEM-based model. By itself, it doesn't vary in length, but there is an approach called arbitrary Lagrangian Eulerian method to sort of allow the mesh to move on the structure. And then I sort of go into the combined effects of this and talk a little bit about some of the extra considerations that you need to think about when you do time integration. Not so many conclusions because it's obviously a work in progress, but yeah. So the motivation, this is building off of some work. So if you were at the Airborne conference last year, you would have saw me presenting a talk where I was comparing ANCF with these quasi-static models, in particular the one by Paul Williams. And in general, ANCF showed some good agreement with these models, so we were quite happy by this. But at that time, we didn't have a cable model that could vary in length, so not so useful for Airborne, but we're getting there. So this work here is trying to build off of that. And so now we can start getting into the theory part of it here. So we have this is the ANCF model, and a lot of these FEM models, what matters is sort of the kinematic description. And so we have this is an element here, so we have the position at the endpoints, but then we also have the slope at the endpoints. And so then we use, instead of like Lagrange shape functions, we use sort of Hermite interpolating polynomials to do the interpolation of the state. The key advantage compared to sort of other FEM models is you don't have any sense of a local frame, and that's why it's called like absolute nodal coordinate formulation. So, and then we're just going to go through, I'm not going to spend too much time about this. This is like standard FEM stuff, but it is kind of important when we start to go back and look at how this ALE approach is applied. So here's our inertial forces, so we do sort of a Galerkin projection of the distributed forces to get the nodal forces, and then you come up with this matrix here, this N transpose N, and that gives you your sort of mass matrix. And the advantage there is it's just dependent just on the shape functions, so it's like time invariant, so you only calculate this once, and then you always use the same mass matrix. So that's why it's kind of advantageous for doing sort of dynamic simulations. Yeah, and now we go into the elastic forces. So we use sort of a Green's strain tensor. And so we have the axial strain there, and then we're sort of using Euler-Bernoulli theory, where we're looking at the curvature of the beam and then trying to get the curvature stress from that. You know, you define a virtual work, and then you get this equation for the elastic forces. And just look at the kappa definition. It is kind of a complicated expression there. We're going to end up doing a lot of derivatives of that kappa definition, so the equations get pretty hairy pretty quickly. Anyways, moving on. So stiffness proportional damping forces, so we basically just take those strain measures, and then we just take the strain measures and do a time derivative of that, okay? So now we've introduced some velocity into our forces, and then this is going to become what's important when we start to consider varying length, okay? So this wasn't so important, but this will become more important, okay? And this is just basically derived, just taking the time derivative of the strain measures there. And then, yeah, so we have applied forces, it's a Galerkin projection, and then we just add up all the forces and they should all equal 0. Okay. So now we're into arbitrary Lagrangian Eulerian formulation. So most FEM models are a Lagrangian formulation, so your grid follows the material. Those of you who are doing CFD work in an Eulerian formulation, so the flow is moving through the grid, but the grid is sort of staying in place. Now, when you try to mix the two, now I'm allowing my grid to move arbitrarily, and I mean like arbitrarily because I can move along my structure, I could keep my structure and then move my structure through the grid. So that's the idea, and then if I could do this, then I could have I could have my kite here, and I could have like equally spaced nodes, and then I could reel out, and I can still have equally spaced nodes. And the idea then is that the number of control points in my simulation are basically constant, and then this becomes something that is sort of a nice property if you want to do design optimization or some kind of optimal control or anything like this. So it always becomes more tricky when you're changing the topology of your simulation. So that's the idea behind it. How does it work? Okay, so what we're doing now with arbitrary Lagrangian, I'll just call it ALE from now on. So the position that the grid has on the structure becomes a variable now. So I've sort of shown basically the same element here, but I've sort of shown the rest of the structure. And where those nodes are placed is a variable that varies in time. And you could have it be something, a simulation result, or you could have it be something pre-scheduled. And so the effect of this variable sort of shows up in the shape function. So normally we have a shape function that is just some canonical polynomial of some sort, in my case Hermite polynomials. And then you have this zeta variable, which is defined according to these S1, S2 variables. And so in classical FEM, we have this like separation where the shape functions deal with your spatial variations, and then your state variables deal with your temporal variations. But when you get ALE involved, then you have temporal dependency in the shape functions, and that's where all the fun stuff kind of comes out. So now we have to look at our kinematics here. So we're mostly interested in the velocity and the acceleration. And because of this time dependence in the shape functions, then we get all these extra Eulerian terms. Does the laser pointer work? Yes. So we still get our standard FEM definitions for velocity and acceleration, but then we get these big ugly terms here. So S dot here is representing the speed of the mesh, and S double dot here is representing the acceleration of the mesh. And there is some familiarity when you're sort of thinking about like rotating systems. You have sort of a Coriolis effect. You have like almost a centrifugal effect. They're not exactly Coriolis and centrifugal effects, but the calculus is the same, so you get the same kind of terms coming out of it. So now we have this kinematic description, and now the work is taking those equations and then reintroducing them back into all the ANCF equations. So I'm not going to go through everything, right? But this is sort of showing an example of how you would sort of apply this ALE to the ANCF, right? So we have this original definition for my inertial forces. So it's basically the acceleration projected onto my shape functions, right? But because my acceleration now has these extra Eulerian terms to account for the mesh motion, so I still recover the original kind of Lagrangian definition, but then I have all these additional kind of effects due to the mesh motion. And I told you this similar thing you have to do with the damping forces, right? So we have this velocity term when we take the time derivative of our strain, but then we have to add this extra Eulerian term to get to now calculate my damping forces. Now the kappa really ugly derivative. Yeah, it's the basic approach. If you want the details, we can share an email. So yeah. And okay, so now the next thing I'm going to talk about is the time integration. And so a lot of the time, so these are the equations that you will have to evaluate when you're doing your time integration. But there is sort of an assumption where these points that you're trying to evolve, the assumption is that they're the same material point, right? From one time step to the next, it's the same material point. So the velocity of this thing at different times. But if my mesh is moving, right, then I'm no longer guaranteed that from the same point from two different time periods is the same material point. So the question is are these equations still valid? So then we have to sort of think about that a little bit. And this is a nice picture to have in your head here. So this is the material dimension, and then this is the time dimension. And if we are reeling out our device, the computational domain is kind of growing, right? Because we're introducing more and more cable into our simulation. And so if I want to do time integration for this point, because this point has moved, because I'm trying to have equal spacing of my nodes, I can't use the previous time history of this point anymore because it's not the same material point. So then I have to do some kind of like interpolation. That's pretty easy. We can go back to doing shape functions and so forth. But also gets a bit more tricky when we're talking about points that happen to be very close to the domain boundary, because if that point didn't exist in the previous time step, what do you do then, right? So then you have to sort of look at what your boundary conditions were at this point. And so we have to introduce some extra complexity to kind of have some spatial interpolation and some temporal interpolation, just to make sure we can still have like a material consistent time integration. But that brings in some new questions, right? So Newmark beta, generalized alpha kind of integration methods. We know what their sort of damping and stability properties are, but are these things going to be changed if we start to have additional sort of numeric effects coming in from all this different interpolation? So also, if we have a moving mesh, are we going to preserve the stability of these integration methods, right? Like if your mesh is moving extremely fast, you might have to change the time step to sort of properly capture everything, right? So there's some research to be done here. So if there's a nerdy grad student, there you go, you have an assignment. But anyways, we're getting to the end of my talk. Just imagine all the beautiful graphs I could have created if that bug in my code did not exist. But I hope all of you have enjoyed this talk. I tried to make some jokes, so it wasn't totally equations. And it's also, anyways, getting into happy hour, so let's end it there. I'm more than happy to take some questions or comments, and yeah, so that's all. Thank you.